Okay, so welcome to today's class. And yesterday we introduced a bit of linear regression, okay, models. But now I want us now to discuss in depth on linear regression. We'll see that is how uh, we can do it step by step, and also we'll discuss different types of that is linear regression. We'll also talk about how we can that is find the best fit line, okay, and also how to optimize our that is our constants in order to get the best that is the best fit line or the best model. We shall of course, under fine tuning or optimization, we are going to use different functions, like we will use a cost function and also the this that is granted descent. After that, we'll that is discuss how we can measure that is model performance, or what are the determinants of that is model performance. Then after that, we'll also discuss about that is the assumptions of linear regression. Because for linear regression to hold, we have some assumptions which we usually make. And then after that, now we'll go to the practical part of it, where we'll be preparing data for a linear regression, okay, and then uh, we'll do the practical, and then we'll be done with what? We'll be done with linear regression. Then next week now do that is the distributions. Okay, that is will next week we'll be purely discussing on that is inferential statistics. Okay, and distribution. Okay, so my plan is to finish um, that is linear regression by tomorrow. Okay, that's my plan. So, of course, we are going to start with the theory part, okay? And under the theory part, of course, I will make sure you understand everything, but I want also you to keep that is to stay focused, so that we may push it a little bit faster. Okay, so basically, yesterday I illustrated this diagram or this graph. Okay, I illustrated this graph, and remember we were drawing that is the line of best fit. And for our case, we used two variables, but here also we are going to use two variables. Okay, that is y and what? And x. Let's assume now y, it is the what? It's the salary. Okay. In fact, I summarized everything yesterday. Let's assume y here is the salary, which is our output. Okay. All right. Yes, or it's also that is our output, also known as that is the dependent variable. Dependent variable. Okay. Then we have x. X is our independent variable. Okay. And in this case, we'll use work experience in years. Okay. Work experience in years to be our what? Independent variable or predictor variable. They are also known as predictor variables. Okay. So what basically this graph shows a plot of work that is work experience in years, okay, and also the salary which you are paying the employees. So linear regression, now from the notes, linear regression performs the task to predict dependent variable. Of course, we are predicting what? We need the output given the independent variable. All right. Yeah, so the independent variable, it's also known as the input. If we have the input, then it is easy for us to get what? The output. Okay, so that's why we are saying that linear regression performs the task to predict a dependent variable. Okay, in this case, y, based on a given independent variable, or based on the input. We usually get the output based on the inputs. Okay. Yeah, so this regression technique finds out a linear relationship between x, which is the input, and y, which is the output. Hence the name what? The linear regression. So basically, here we are trying to get that is a linear relationship. Okay, a linear relationship. And when we'll come to the assumption, you will find this is the major assumption. Okay, so if maybe you want to create a model, okay, that is using a linear regression method, we usually assume that there must be a linear relationship between what? Between the two variables which we are taking into account. Okay, yeah, so that's why we are saying now there must be a linear relationship, okay, for it to be named as a linear regression. So like in the figure above, you can see x, the input, is the work experience in years, of course, and y output is the salary of the person. The regression line is the best fit line of the what? Of the model. Because you can see we have these data points. Okay. Like for example, you can see we have this data point, we have these data points, we have these data points. But when you do the regression, it plots, okay, the line of best fit, okay, the line of the best fit. So this is the line of best fit, okay. And then we have what? We have some that is error term, okay, which are known as that is vertical deviation. They are also known as vertical deviation, which is the difference between the data point to the regression line. You can see the distance between the that is the points which are not are not crossed by the what? By the line. Okay, so you can see we have that distance. Okay, both positive and negative. All right, because like for example, if you take this point, okay, if you take this point and minus this point, definitely you will get what? A negative, because this point lies lower compared to a point along what? A point along the line of best fit. Okay.
Excuse.
Yes.
I don't know whether others can see, but I can see. Yes, I can see the screen, but can't see the plot where you're. That's clear. That's
That's
okay.
clear. Okay. Yeah. So that is the distance between what? The distance between this point to the that is a line of best fit. It's now what we call what? The error term. Okay. Yes, I know. In some models, we were calling in regression, we were calling the error term as what? It's as the epsilon, okay, or the vertical deviation, okay. Yeah, so remember that you, let's say assume this model, it's given by mx plus c plus what? Epsilon. This epsilon is what? It's the error term. And the error term, it's the distance between the data points which are far from the what? Regression or far away from the line of best fit. Okay, so that distance is now what we call that is the error term. Okay, good. Now let's continue. I hope we are clear on this diagram. That is the other thing I discussed about maybe when we extrapolate, then this is what? This is our C, okay? This is our C because it is the what? The y-intercept. Then if we get the, that is the, what do we call it? The slope or the gradient of the graph or of the line, then it becomes what? Our that is constant attached to our independent variable. Okay, and then we have yeah, I think those were the major things. This constant. We were talking about these constants. All right, good. Now, let's assume this model. This is the same model which I did for that is for the line of best fit because this is the now the y-intercept and this is what? The gradient. That is the constant attached to the what? To the independent variable or to the x variable. What they have just done is just to interchange. So like for example, in my case, it will be y is equals to c plus mx. It is the same thing. Okay? Yes. Good. But now we can include this plus or minus because this can be plus or it can be what? It can be a minus. But this cannot never be what? This cannot be a minus. Slope can't be that is a negative. All right. I hope now we are good up to that point. We can now that is continue. All right. So while training the model, okay, let's go to the hypothesis function for the that is for the linear regression. This is now the hypothesis function. That is, we have X as our what? Input data or training data. That is training data you will mostly that is learn when you will be dealing with what? Machine learning. When you will be creating that is predictive that is models under what? Under machine learning using Python language. Okay, so we usually have the input data, and the input data is always divided into two. We have training data and then we have also testing data. Okay, like for example, if you have a model, okay, so let's say you have some images here. Okay, let me. So let's say we have some images here. Okay, don't know what I'm really drawing here, but let me go with this. Okay, let's say this is the some objects what? Some objects data. And we want to create a model, okay? We want to create a model that will give us the name of the what? This is the model. The name of the object. Like for example, you can see we have what? This is a triangle, this is a circle, this is a rectangle. This is an inverted what? Triangle. Meaning you can have these objects in what? In different maybe positions. Okay. But the that is our model will define what? Our model will define that is will define the objects. Okay, so if we create or if we that is collect, let's say, a million set of these objects in different shape, in different color, okay, in different size, then we will have a share. Like, let's say we usually use that is the 80 percent, the 20% rule. Okay, whereby we will use now this data, 80% of the data, to train the model. Okay, and use 20% of the data to test what? The model. That's why we usually, now I'm talking about the two different inputs, like training data and testing data. But majorly this will discuss in depth, that is, and we'll discuss this more, and uh, machine learning. Okay, under the machine learning topic, that is topic. All right, so then we have why it's our what? It's our output. Okay, why it is our output. In fact, in short, the labels. Like, for example, if now we that is run this object, okay, this object through our what? Model, classification model, then it will what? It will that is return what? Maybe a triangle. It will return it's a triangle. Okay, so it will label, because when we were inputting this data, we were labeling them. Okay, but basically consider that as what? That as an as the outcome. All right. So when training the model, it fits the best line to predict the value of y for a given value of x. Yes, because for us to predict, we have we need what? We need that is the predictor variables. Okay, that is the independent variable x. All right. Then the model gets the best regression fit line by finding the best values of what? Values of the constants. Remember, these are our constants there. We have the y-intercept and we have the gradient. Okay, so for us to get the best regression fit line, we also have to optimize what? We also have to optimize our that is our constants. Okay, and that is the process of optimizing the constants we shall discuss. We have different that is methods to do that. We can use different functions like the cost function, okay, to make sure we get the what? The best that is the best constants. Okay, so once we find the best constants, okay, we can now get the best fit line. So when we are finally using our model for prediction, it will predict the value of y for the input value of what? Value of x. All right. Now let's come to types of linear regression. So we have simple linear regression, multiple linear regression. For simple linear regression, it's a model where we have what? Where we have only that is one independent variable. Like, for example, okay, let's assume now we are building a model to predict what? The amount of salary. Okay, so let's say our output will be what? Salary. Okay, and what are we using? Then we have what? Our constants here. Let's say we have constant, the first constant. Okay, multiply by the x what? That is the x variable or the independent variable. And this, in this case, we'll use what? Work experience as what? As our independent variable. and then plus the other constant, and then we can also add the error term, that is the epsilon. So in this case, okay, I can even call this theta 2. Okay, so in this case you can see we only have one independent variable. So in that case, it becomes what? Simple linear regression. What about like if we were to add another factor like also the level of education, okay, or really what impacts the salary majorly? We have the work experience in years. The other thing is um, how can we compute the level of education? How can we really that is compute? Okay, but for that, maybe we can now, since it is a qualitative data, we can now change it to what? We can change it to quantitative. The same way for work experience, we'll now use maybe yes. Okay, we can decide to say high school to be represented by 1, degree to be represented by 2, then masters maybe to be represented by 3. Okay, yes, as the education level increases, we increase what? Also our values. Okay, so now we will be having two independent variables. Like for example, it will be salary, okay, will be equal to that is theta 1 multiplied by x1, whereby x1 is what? Work experience, okay, plus theta 2, okay, multiply by x2, whereby x2 is what? X2 it is the education level, okay. So then plus maybe the error term epsilon. So with this case, you can see we have what? With this case, we have two variables, okay, or two independent variables, x1 and what? X2. All right. So majorly that's the difference. For simple linear regression, we have single or one independent variable. For multiple linear regression, we have more than one. Okay, more than one, because you can find a model with even three independent variables. Okay. All right. So if I'm single independent variable, okay, so simple linear regression. So if a single independent variable is used to predict the value of the numerical dependent variable, then such a linear regression algorithm is known as what? Is known as simple linear regression. Correct. So what about the multiple linear regression? So if more than one, okay, meaning it can be it's two um, going that is going forward, it then if more than one independent variable is used to predict the maybe the outcome or the dependent variable, then such a linear regression algorithm is now called what? Multiple linear regression. Okay, because we have more than one independent variables. Okay, now let's come also to the linear regression line. Okay, remember we have a positive linear regression line and also a negative linear regression line. Like for example, this is what? This is a positive linear regression. Why? As because as y increases, so does what? So does the x. Okay, if it is a negative, when one is increasing, the other one will be decreasing. Okay, so let me illustrate that. Like for example, we have this is a positive uh, Let me make it a little bit straight. Okay, we have that and we have this. Okay, so this is a positive linear regression line. This is a negative linear regression line. We have y, we have what? X. We have x, we have y. Let's assume we have maybe 10, we have 20, and here we have 5, and here we have 10. Okay, let's assume also here we have 10, here we have 20. Okay, here we have 5, here we have what? 10. Okay, now let's go with the positive. So let's assume we are let's start with this value here. Okay, and also this value. So you can see as we are increasing, the value of y, you can see we've increased it from 10 to 20. Okay, as we are increasing the value of what? Of the y, you can see we are also increasing the value of what? We are also increasing the value of x. Why? Let's assume the first one, we had y was 10. Okay, and x was what? X was 5 and y was 10. Okay, we increase the value of y to what? To 20. Or we can say we increase the value of, this is the best language, we increase the value of x from 5 to 10. Okay, so in turn you can see the value of what? The value of y increased from now 10 to what? To 20. So you can see at the end we are having a positive, that is regression line. Why? Because as y increases, also does the x value. But let's now come to this case. Okay, so we have this point and we have this point. Let's assume even here it's 40. Okay, and let's assume here, I'm just going to assume it is 20. Now let's take the 2 points. Okay, so let's increase what? Let's increase, um, just a minute. So let's increase the value of what? The value of x. So you can see when we increase the value of x, okay, we are reducing. You can see we are reducing the value of what? The value of y. Because at first, at this point, when x is 5, y is 40. Okay, when x now it is 20, y it is something less than 40. Okay, so we can conclude that as we are increasing the value of x, we are now reducing the value of what? A value of y. And that's why we are talking of what? Of a negative linear regression. Let's check on that. So a linear line showing the relationship between the dependent and independent variable, it's called a regression line. A regression line can show two types of relationships. Okay, relationship. That is a positive linear relationship, like if the dependent variable increases on what? On y-axis, and the independent variable increases on the x-axis, then such a relationship is termed as what? A positive linear relationship. What about the negative relationship? So if the dependent variable decreases on the y-axis, okay, and the independent variable is increasing, so you can see it as one is decreasing, the other one is what? Is increasing. Then such a relationship is known as what? A linear relationship. Okay, so we have those two types of what? Linear relationship. Okay, any question maybe up to that point? I need questions. Any suggestion? Okay, then it means we are all good and we are understanding everything, which is very very good. Okay, so I want us now to go to the next slide, and then after that we can proceed maybe for a break, and then later we'll discuss about that is the assumptions. Okay, so our last that is point today, it will be what? It will be now the this point. Okay, that will be our last point for today, so that tomorrow we might do the that is the practicals. Okay, tomorrow will be purely practicals, and these are just some theories here. These will be what? A theory. This is a theory, as well as this without practical. This will be a theory without a practical. The other ones we have already discussed, like the correlation analysis, the negative correlation, positive, zero correlation, we discussed that. Correlation coefficient, we discussed that, and even that is calculated, the same as correlation analysis. We discussed this. We discussed this yesterday. Then, after we finish now the practical, we shall close with the. Um, in fact, not closing, because these steps, we will discuss them tomorrow. Because they are the steps which we will, which are being used or to prepare your data before what? Before doing now the regression. All right, good. Now let's go to the finding the best fit line. Okay, so when working with linear regression, our main goal is to find the best fit line. That means we have what? We have minimized the error term. Okay, we have minimized the error term. Like it's almost every point. It's what? It's close to the. It's either on the crossed by the line, or it's close to the what? To the regression line, meaning our error terms have been minimized. Not in this case. Like for example, you might find this is our that is our baseline. Okay, but we are having some that is a large error terms. Okay, like we are having some points, data points which are far away from what? Which are far away from the regression that is line. Okay, yes, good. Now that's our objective as we do regression. Okay, our aim is to get what? It is to get the best. That is to it's to get the best line. Okay, uh, fit. Good. So to find the best fit line, that means the error between the predicted value, that is values, and actual values should be minimized. So the best fit line will have the least error. Of course, in this case, we will have the least error. So the different values for weights or the coefficient of lines gives a different line of regression. So we need to calculate the best values for that is for the weights. Okay, these are the weights. A0, A1. They are just the weights. Okay, and to do so, we usually use that is the cost function. And in our case, the major that is the major um, that is the major cost function which we are going to use. It is the mean squared error. Mean squared error is the cost function which we majorly use to obtain, okay, to obtain the best the best what the best value of our coefficients. Okay, all right. So the different values for weights or coefficients of lines gives different line of regression, and the cost function is used to estimate the value of the coefficient for the best fit. Okay, so what is the function? What is the work of cost function? So cost function optimizes the regression coefficients or the weights. It optimizes or it finds the best, okay, coefficients. It measures how a linear regression model is what? It's performing. We can use the cost function to find the accuracy of the mapping function, which maps the input variable to the output variable. And that is the cost, the mapping function, which we majorly use, or it is also known as the hypothesis function. Okay, like for our case here, we had the hypothesis function for the linear regression, which was this. Okay, so we usually use this mapping function, okay, to now obtain what? To now obtain the accuracy of what? Of the cost function. So for linear regression, we majorly use mean squared error cost function, which is the average mean error, or that is which is the average of the squared error occurred between the predicted values and the actual values. Okay, yes. So for this cost function, majorly in Excel, we can't optimize regression analysis, but in Python, okay, when you will be that is computing the accuracy of your model, okay, you will use I think they are three functions, okay. They are three cost functions or function which are used to measure the accuracy. That is the mean squared error, okay. The other one, it is the root, is it the root squared uh, mean error? I can't remember this, but we have the root squared mean error, and then the third I can't remember the third function, but they are three. Okay, so you'll do it practically using Python. So you can note it down, and then during the Python or the linear regression using Python, that is in machine learning, then you can be able to remember that. And in just in case maybe the tutor skips maybe or forgets, you can you can ask. But it's not easy to that is to forget, because this is very core. Why? Because after you create your model, you have to test for accuracy. Okay? You have to test for accuracy. Then, but for that is uh, in 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 Excel, we will use a coefficient of determination to measure the that is the performance of the model, to see if our model it's we can be confident about our model, or is it performing well in terms of accuracy. Okay, so I want to give you an example. So let's assume we have the that is the original values of y, that is the yi's. Okay, then we will minus with what? With y at. These are the actual values of what? These are the actual values of y's. These are the predicted variables. That is values of y. Meaning y at will be equal to that is a, maybe ax plus b. That is the equation, or the linear the simple linear regression equation. Okay, so in simple format, we can say now the cost function, or that is this cost function mse, it's given by, remember it is squared. Okay, so we will have to what, to square here, so it will be given by y i's, okay, or we can say it is summation. We can say summation of y i's minus y at squared, which is also that is summation of y i's minus into ax plus what, plus b, and then we will square all this. So this is the mean squared error. So let's try and check that. And remember to divide by what? By 1 over n. Okay? Always remember to also divide by n here, because uh, it's like just saying multiply by 1 over n. So you can simply divide by what? By n. Okay, can simply divide by that is by n. Okay, so for the above linear equation, okay, the mean squared error can be calculated as follows. Okay, we have that is a summation of y i's minus y at. This is y at, or the predicted what, values, then divide by what? Divide by n, where n is the total number of observation, yi's they are actual values, and what? This, or y at, is the predicted variable. And then we have the residuals. It's like you are saying plus epsilon, whereby the residuals they are also the error terms, all the vertical deviations, and it's the distance between the actual value and the predicted value. Okay, so the distance between the actual value and the predicted value, it's what? It's the residual. If the observed points are far away from the regression line, then the residual will be I. Remember I said this when I was illustrating here. Okay, as I was illustrating here, points far away from the regression line and points close to the regression line. So we are saying that if the observed points, okay, are far from the regression line, then the residual will be what? Will be I. And so cost function will also be I. And if we have a I cost function, then it means our model, it's weak. It's not good. Okay? Why? Because the cost, for us to have a good model, the cost function should be very small. The smaller the cost function, the better our model. Don't forget that. Okay? So um, if the scatter points are close to the regression, then the residual will be small, and hence the cost function will be what? Will be small. Okay? Yes. So if you see a small cost function, the better. All right. All right. Now I want us to go through the descent. That is the granted descent and the model performance, then go for like a 10 minutes break, and we shall finish to refresh as I take a cup of that is a glass of water, then we shall finish with the assumptions of linear regression. Also, I will share the notes. These ones, or I think I shared all the notes. Yes, I shared all the notes with you. So these notes should be with you. All right, so the gradient descent. Now, in turn now, remember we've said the cost function should be what? Should be very small, okay? For us to get what? The best fit line, okay? Now, what about the gradient descent? Now the gradient descent tries to reduce the cost function or tries to minimize the cost function. And remember, when we are that is minimizing the cost function, we are making our model to be more and more better. Okay, so gradient descent is used to minimize the mean squared error. Okay, and for mean squared error, we've said it is what? It is what we call the cost function. Okay, so it gradient descent minimizes the mean squared error by calculating the gradient of the cost function. So a regression model uses a gradient descent to update the coefficients of the line by reducing the what? The cost functions. Okay? Yes, as I had told you. All right? It is done by a random selection of values of coefficient and then updating the values to reach what? To reach that is the cost function. So it is kind of simulation. We try to randomize or to randomly select the value of what? Coefficients. Okay, so we try to maybe to that is to select randomly the value of what? Of our constants. Okay, and see that is the constant which will give us that is the smallest what? The smallest error term. Okay, and with that we'll be that is minimizing, we'll be minimizing the that is the cost function. Okay, using the gradient descent method. Then we have the model performance, the R squared method. This is how we do what? We calculate or we measure the performance of our model. The R squared, also known as coefficient of determination for simple linear regression or coefficient of multiple that is determination under what? Under multiple regression. So the model performance, the goodness of it that is determines how the linear regression fits the what? Sets of observations. Okay, like for example, we have the data points and we are trying to see how this line of best fit fits our what? Our data points. Okay, yes, and remember our data points are in what? These coordinates y, x, and what? X and y. Okay, so the process of finding the best model out of various model it's known as optimization, and it can be achieved by the below method, that is the R squared method. R squared method is a statistical method that determines the goodness of what? Of it of our regression line. Okay, it measures the strength of the relationship between the dependent variable and the independent variable from a scale of 0 to 100%. Okay, yes. So if our model is 90% good or fits 90% of our data points, okay, then we can say we will be having 90% accuracy of what? Of that model which we've created or we've built. Right. So the higher the value of R squared, determines the less difference between the predicted values and the actual values, meaning we will have a small error term. Okay, we'll have a very small error term. Hence, this will represent what? A good model. R squared method is also known as, or it's also called, coefficient of determination for simple linear regression, or coefficient of multiple determination for multiple regression. And I will now share that is tomorrow I will share the formula that we use to calculate what? To calculate the R squared. It's always a very huge, that is formula. I think it's always that is summation of x and y minus summation of x multiply by summation of y, okay, divide by square root of that is summation of x i's minus x bar squared divide by n multiply by square root of, but we will confirm this. We will confirm this. This should be y. We will confirm this and then I will let you know tomorrow. But it's such a formula. It's big formula. It's a big formula. That which is used to calculate what? The R squared. Okay? All right. I think we can proceed to a 15 minutes break. Uh, then to conclude on the assumptions of linear regression. They are only two slides, and then we will call it a class. So let's go to a break of that is 15 minutes so that I can also take a glass of water. Otherwise, thank you. Let's meet then.